Hello, everyone, and welcome to CodeCast by STL Tech Talk, where we are going to bring you the content you want and need: instructional, informative, unique, and insightful commentary on programming and technology. My name is JJ Hammond, and I'm joined tonight by two coding experts. Up first, our guest, the lead software engineer for Upside Financial, and he's the startup veteran project manager that everybody wishes they had. The one, the only, the greatest guy ever, Brad Urani. Hello, Brad, and welcome to the show.
Thank you, JJ. That's quite an honor. I appreciate those accolades.
Well, yeah, dude, I'm telling you, there's plenty of people that I can't stand. You're not on that list. But tonight, I am joined with my good friend and fellow co-host, striving to bring developer knowledge to the masses, and spent the last 20 years architecting and implementing highly scalable ASP.NET applications, our very own Gus Emery. Hello, Gus.
Hey, JJ, I know I'm right at the top of the list of the people you can't stand, so thank you very much.
Well, I didn't say that. You did. No. And go follow this show and support CodeCast by finding us on Twitter, #CodeCast. Somebody else was using that the other day, and I said, that's funny you use that because we use that for this thing, and you're more than welcome to come on the show. They haven't replied to me, but we'll see what happens. Or at CodeCast, STL is another good way. And don't forget, you can interact with the show by sending us feedback to contact@stltechtalk.com. And we want to take a moment to thank the sponsors of the show, Inertia Software. Remind me to change this later, JJ. Okay, Gus, I'm reminding you now. Creating cutting-edge, highly scalable Microsoft technological solutions to the energy industry and much more. Visit inertia-software.com or hit Gus up for more information. And Tech Systems. Do you want to advance your IT career? Of course you do, but you don't want to submit to hundreds of resumes on online job boards in the hopes of finding your next job. Your solution is simple. Tech Systems is a leading IT staffing provider in the U.S. and is ready to be your career partner. Their goal is to help you achieve your professional and personal goals. Contact a local recruiter today, techsystems.com/St. Louis. That's teksystems.com/St. Louis. So without further ado, let's get into the reason why we're all here tonight. And Brad, that is for you to give this awesome presentation. So why don't you go ahead? I'm going to tee it up for you. Tell us what's going on.
We're going to talk about functional Ruby tonight, functional programming in Ruby. This is a talk I gave at the CodeMash conference in Ohio early this year. Thought I'd share this with you all. Functional programming is a very hot subject, and I know a lot of people want to learn about it. So I'm going to do my best here to explain what exactly that is by demonstration. So here we go.
Demo
Awesome.
time.
Can't wait to hear this.
So that's me. My name is Brad Urani. I'm Director of Engineering at Upside. We're a financial tech startup in St. Louis, Missouri. We are creating the future of online investing. Follow me on Twitter, Brad Urani. Let's check out my website, fractalbanana.com. So functional programming, right? I think a lot of people who are big object-oriented programmers, when they first start to read and hear about functional programming, I think they sometimes it can be a little hard to figure out exactly what it is and what's so special about it, because a lot of the techniques in functional programming are things you're probably already doing, which are things like using lambda expressions, higher-order functions, and I'll explain what those are. But what we have at the heart here is the style of programming, right? It avoids state and mutable data, right? And basically what that means is, the goal in functional programming is to set variables, right, and not change them after you've set them. And of course, anytime you write a program, you have to change variables at some point or another. But the goal of functional programming is to limit that as much as possible into as few places as possible where you're actually changing the data. And how we get there, really, and what makes functional programming is a combination of techniques, and some of these are probably techniques you're used to, and some of them may be new to you, right? So let's, here's another definition, right? Functional programming is merely a discipline that takes what many consider a good idea to its logical endpoint. So a lot of these techniques I'm going to show you are what you probably already know as best practices, right? When you take all of them, these techniques, you combine them, and you're strict about how you follow them, right? Then you've actually achieved functional programming. Just to sort of compare and contrast here, object-oriented programming, it's got some strong points here. Domain modeling, right? Basically, creating classes that match the way your data is, that's domain modeling. So polymorphic data, when you've got a class that's a person, and then you've got a subclass teacher and a subclass student, right? That's great application of object-oriented programming, right? Using data associations like with an object relational mapper, composing things, like you've got a class that represents a kitchen, and then a class that represents a refrigerator, and you're composing things using objects, right? All wonderful applications. They're good for modularity and, of course, making like user interface components, right? Functional programming is more of a way to arrange logic in a program, right? So it's less about how you're modeling your data and more how you're arranging your logic. So great for business logic, which is every application needs business logic, right? Data transformation, things like ETL, data processing, for making dashboards, especially real-time, including real-time. Algorithms can all be written in a purely functional style, and it's especially great for parallel algorithms because of the way it limits mutations to variables, right, makes it more thread safe. So
Right.
especially concurrent multi-threaded programming are all wonderful applications for functional programming. So in other words, functional programming, it replaces the procedural parts of your code, right, and it complements the object-oriented code. So we're not trying to do away with OO, right? We're trying to do probably a little less OO and use functional in places where we're worried about how to compose all the logic that we're going to use.
Okay, gotcha.
Yeah.
And we should say to our visual audience that you do have a slide deck that you're going to be showing off too when you share your screen.
Oh, shit. I thought I was sharing it.
That's awesome, Brad.
There you go.
Well, we can flip back to it now.
Okay, here we go.
And scene.
Pardon my language. All right.
That's what editors are for.
There we go, Brad. I can see it.
Oh my God. Well, anyway, thankfully those were all words, but yeah, so we went through all that kind of stuff. Okay. So what are our actual? Let me make sure I got it. Okay. So in general, right, just to summarize what I just said, object-oriented code, right, it excels at composing data, right, and functional programming is about composing logic, and that's my own definition there. So what are these techniques I'm talking about, right? What are these techniques where we're actually using that make a program a functional program? And we have to start with immutable data structures, and those are just your basic lists and stacks and queues and all that stuff, but in a way that once you make them, they can't be changed, right? Higher order functions, that means those are functions that take other functions as arguments or return functions, right? So your map, your reduce, those are higher order functions, right? Partial function application. I won't go into detail of these now because I'm going to get into them, but these little check marks, these represent basically what Ruby already has built in. Immutable data structures, right? That little squiggle, that's because we need a third-party gem in order to achieve that. Ruby doesn't support that out of the box. Specifically, we need a certain types of functional data structures that aren't part of the core Ruby libraries. Right. These other techniques, the ones with the green checks, Ruby supports very well. And then a few things missing because Ruby is not a purely functional language, right? Our lazy evaluation and pattern matching, but we can get pretty close to a pure functional style without those things. And I'm going to talk more about what this stuff means. So this is not a new idea, right? Functional programming is old, right? The key paper was in 1977, where the functional style got its name, or functional programming got its name. People say that Lisp was the first one, but they say that every time someone invents something, they say, oh, Lisp did it first, which, yeah, take it with a grain of salt. But what happened was, all this great progress was made in functional programming in the 70s and 80s. In the 90s, something happened, which is Java just blew up on the scene, and basically ruined 20 years of progress in functional programming. Java's not a functional language. It's terrible. It doesn't support higher order functions, and so it really set the functional programming movement back. By some miracle, JavaScript has functional features, and Ruby too, even though it came out about the same time. But now we're sort of going through this functional renaissance with things like Scala are getting real popular. Ruby on Rails, though it's not really functional, at least sparked interest in those Lambda expressions again in the form of blocks, right? And then now, of course, Clojure, Haskell, those things are the hot stuff. C# finally got Lambdas, and now Java in 2014, great, thanks, great. Now you've got Lambda expressions, Java. Good job. But Google's Go is very unfunctional too, and I don't know why people are falling in love with that language all of a sudden, because I think it's a mistake. So here are these techniques, right? Okay, immutability in Ruby, right? We need to do functional programming. We need an immutable list, and you know, the two approaches is you could just use a normal Ruby list and just not mutate it, use a little discipline, which is perfectly acceptable, or we can use a third-party gem, and the one I use is called Hamster, which gives us all our lists and stuff in a mutable form, right? I do want to mention this because Ruby supports a .freeze method. This does freeze a list and make it a mutable list. It's not exactly what we need, though. While it is immutable, it's not persistent, and persistent is a term from functional programming. It doesn't mean what it sounds like it should mean. Persistent is something that's both immutable but also memory efficient when you clone it, right? And I'm going to explain more about that. So higher order functions, these are functions that take functions as arguments, right? So I start with this array 1, 2, 3, and I'm calling map on it, right? This is Ruby's block syntax here, you know, similar to a lambda expression if you use C# or Python or something like that. I'm basically squaring every element in this list, right? So I start with 1, 2, 3, and we get 1, 4, 9. So this map function is taking another function in the form of that block there as an argument. Here's another one, reduce, right? We take 1, 2, 3, and accumulator is the function that, well, if you use Ruby a lot, you probably already know this stuff, so I'll go over it quickly. So I'll go through it fast, but basically reduce or inject takes a list and boils it down to one value, right? But you can see that we're passing a function to another function. This block here is a function. Sorry. Okay, so here we've got some hashes, right? Here's another example of map, right? I'm just creating a list full of hashes here, first name, last name, and I'm mapping and putting the first name and last name together, right? We get back an array of the first and last name together, right? So this makes nice, clean, concise code. Here's another example, and I put this one in because it's going to play a part in my later demonstration. I'm starting with just a list 1, 2, 3. That comes through this as an argument num to my block function, right? And for each one of those, I'm returning an array with 3 values in it, right? That gives us an array of arrays. Follow me there, guys?
We are following and ready.
Cool. We definitely are. That makes a lot of sense.
Yeah, okay. So if you want this, if you didn't want that, right, if you didn't want them nested, we have this function flatMap, right, which would combine all the arrays together, right, so I get one flat array. Remember this because this is important in the demo. So Ruby does have a few different ways to do higher order functions. They've got this block syntax, right? They've got 2 versions of that, the single line version and the multi-line version, but they're the same thing, right? Quick side note, to get into some technical terms real fast, don't worry if you gloss over this part. The Ruby block syntax is not referentially transparent. And the reason it's not is because you can put an early return statement in it and it will return out of the containing function. If you're doing functional programming, just make sure you don't put return statements in your blocks. They also have these lambdas, right? And this is similar to like in JavaScript how you can assign a function to a variable. So here amount is the parameter, right? And then that amount times 1.06, that's the function body. And then I'm assigning it to the variable sales tax, right? And this is purely functional in style. This is purely functional, but those are technicalities. So one of the things we avoid in functional programming is a side effect, right? So this is the kind of pattern you see typically in object-oriented programming, right? Where I've got this method steal cookies, right? And that is mutating a variable pent-up aggression, right? That is a side effect, and this is what we try to avoid in functional programming, because I'm mutating a variable within the class and also returning a value, which is, hey, give those back. As Bertrand Meyer said, who's a functional programming pioneer, methods should return a value if they are referentially transparent and hence presents no side effects. That's more lingo. Don't worry if you're not up on the lingo. And I will mention that one of the things that I do think makes functional programming a little difficult for some people to like try to wrap their heads around is that the lingo is very odd. The vocabulary comes from weird branches of mathematics, such as category theory and type theory, and the terms sound like things they shouldn't talk about. So don't worry if you're off put by functional programming lingo. We all are. All right. And one thing I want to mention, just going back to this, right, is how do you unit test this class, right? If I'm going to unit test the method steals cookies, it's real easy to write a test that checks that the return value is what I expect it to be. A little more difficult, right, to check that I incremented pent-up aggression, right? You have to pull some tricks in order to write a clean unit test. So by avoiding side effects in this code, like this in your code definitely becomes more testable. As Daniel Spiewik said, he's a Scala contributor. I write functional code out of self-preservation because I don't know how to test stateful imperative code. So here's an example of another type of higher order function. This is a function that returns another function, right? So you pass in a city state to my sales tax function. I'm getting back a lambda, which is a function, right? I'm getting back a function that takes total as an argument, right, and returns the result of this little mathematical calculation. So two types of higher order functions, right? Functions that take functions as arguments, functions that return functions when they're called. And Ruby does both. So another example of this, why this is so great, I've made a little isPrime function, right? And we pass in a number, and we get back a Boolean, true or false, or whether that is prime. Don't worry if you've forgotten your math, you know, and what prime numbers and all that business. It's not important for this demonstration. But you can see that when I make this, when I make this function here, well, I can call this using another higher order function. Select. Select is the same as filter, by the way, or where if you're a .NET programmer. I'm calling this function isPrime from my select here, and I'm getting a list of prime numbers. Well, that's all good, and that's all nice and good. Remember this one line right here, because here's the Java version. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You know, it's about 12 lines, where it's one line in Ruby. So that makes you appreciate that those higher order functions are in fact a really, really powerful technique to clean up your code, right?
Yeah, because that's 12 lines you can make a mistake. Exactly.
And notice here where this is a list, results.add, and if you were writing that in parallel, you'd have a thread problems with that. Okay. So that's all fine and good, but what if we want the first 10,000 prime numbers? So instead of prime numbers up to 10,000 or whatever, I want the first 10,000 prime numbers. Well, I could do this, right? I could just calculate all the ones up to 1 billion, you know, and I'd probably get the first 10,000, but I don't really know. The 10,000th prime number, is that 100,000, is a million, is a billion? I don't really know where to stop this calculation. You see what I mean? I'm not really sure, right? So here we introduce, to fix this problem, because this one is calculating all the primes up to 1 billion. That's not what I want, right? It's calculating way, 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 way more primes than I need to, right? So the way we fix that, here's the exact same code, but I put this lazy in the middle. Whoops, sorry. I put this lazy in the middle. So what this is doing is it's not running this code right right at the end of this. In fact, you can see the return. What I get back here is this class enumerator. Basically, what I've done is I've created a function, passed it all its arguments, right? Chained on a take 1,000 at the end, right, to take the first 1,000 elements in the sequence, right? Yet I haven't actually run it yet. So what's nice is about this is when I do run it by putting a 2a at the end, which converts it to an array, right? Instead of calculating all the primes from 1 to 1 billion, I'll only get the first 1,000, which is what I wanted. So lazy evaluation, right? This is a core feature of functional programming language, and something you want to do to make your code cleaner. It solves that problem, and we're going to see more laziness in my demonstration also. So does that kind of all make sense to you guys? Those I've outlined a few techniques: immutable lists,
totally.
Higher order functions, and lazy evaluation.
Right? I like the lazy evaluation. It's really nice.
Yeah, it makes total sense to me.
Yeah,
that's awesome.
Cool. So now we're going to use these techniques, and I'm actually going to solve a problem, right? And the problem, this is a cool little project. I first ran across this one. I took an online class. It's on Coursera. It's called The Principles of Functional Programming in Scala. And it's taught by Martin Odersky, who's the inventor of Scala. Scala is a really kick-ass functional language. Pardon all my cursing tonight, gentlemen. I don't know what's wrong with me.
It's all good.
Yeah. Scala is a really, really, really neat functional language. It's sort of the new Java, and it's way better and much improved. And the language inventor did this great Coursera course. And this is the final project. So I did this first in Scala. I've now converted it to Ruby because I thought, I kind of had Scala envy. I have to work in Ruby every day, and I kind of had Scala envy, and I was like, geez, couldn't I make my Ruby act like Scala? So I rewrote the program in Ruby, and I'm going to share that with you now. But what the program does is it solves a video game. So Block Stores is an old Flash game. You guys remember Flash games?
Oh yeah, it's been a long time, but yeah.
So I did not make this Flash game, right? But what I made is a solver that efficiently solves this game. I'll show you what I mean. I hope I don't get a bug. Flash had a big vulnerability that was just recently patched. I hope I don't get a bug just by using this. All right, so I'm this big like granite piece here, and the goal is I have to move this block and get it down here into this hole, right? If I fall off, I lose, right? And I have to try again. The goal is to yoink. The goal is to get this block in the hole just like that, right? So this game also has these little bridges. My simulation does not have these little bridges. Oops, I got to stand straight up on that one. Oh boy. What can I do here? Aha. So have a look at this level now, right here. Remember what it looks like. Susan. Remember what this level looks like. So there it is right there. There's an ASCII representation, right? So the S is where my big granite piece starts. The G, the goal, is the hole I'm trying to go to, and the O's are the board, right? Looks the same.
Okay.
Okay, same board, right? When I run this program, what happens is it gives me the shortest route to the goal.
Nice.
Nice.
That's actually level 2. RB. So there's the answer right there. You all can see that, right? And if I put these side by side, yikes. You can see that I just have to go, all right, here we go. Right, up, right, up, left, down, right, up, right, down, right, up. Oh boy, wait, I'm on the wrong level. Hold on a second. Wait, no, I'm not. I apologize. Yeah, that looks right. That looks right. Right. That looks right. Let me try that again. Okay, try again. Right, up, right. Oops. Right, up, right, up, left, down, right, up, right, down, right. I think I missed it. Hold on. Let me try a different level real quick. I think these levels might have changed on me. Five, 2, 4, 3, 8, 3. All right, let's try this one. So here we have a more complicated level. There's my ASCII representation of it. That is level 3. There's my answer. Here we go. Right, down, right, down, right, up, left, up, left, up, right, down, left, up, right, down, right. Ha! Thank God, I'm not crazy. All right, so what I did...
Holy cow, look at that.
Yeah, nice, huh?
Dun, 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 dun.
There you go.
There we go. So the program solves the shortest route, and that is, in fact, the shortest route. I promise you that, to solve that level. So let's see. So this is a program. This program is a what it is a recursive tree search, right? So imagine I'm up here. This represents the place that the block starts at, right? From that starting block, there are 4 possible moves I could take: left, right, up, or down, right? So this tree shows the possibilities. From each of those, there are 4 more possible moves: left, right, up, or down, that I could take, right? So I have a tree of possibilities I need to explore. The red boxes here indicate ones that are either where the block has fallen off the board, right, or where they've hit a position that you've already hit before. So what we're going to do is write an algorithm that tests out all these possibilities in this order, right, from the start, looping in this sort of like snake-like way through these possibilities of this tree, right, to try to arrive at the first answer, right? So that's basically what my function program does. And the way we're going to do that, right, is so imagine you're at the start, right? That start is a node in this tree, right? If I flat map, right, we remember flat map from my demonstration, I get back an array with 4 moves. So basically I'm going to take the array left, right, up, down, and I'm going to flat map it to get to the next possible moves, right? To get the kind of second row in the tree, right, of the sort of the possibilities I'm going to explore, the possible moves that I can take that may or may not lead me to the goal. If I take those 4, right, and I flat map each of these 4 to left, right, up, down, I get 16 possibilities, right, in a single array, right? So I get this array on the bottom. So I'm going to be using these higher order functions, this functional programming, to get this third row in the tree. And then what I'm going to do is, so basically I'm taking a list of 1 item, a list of 4 items, and a list of 16 items, right? Then I'm going to use a function called concat, which actually strings them together. So that I'm going to take this tree and basically flatten it out and evaluate it in the order of this green line until I find the answer. At the end of the day, basically, I'm traversing the moves in this order until I get the answer. So there are a few different ways you could try to do this, right? The interesting thing is if I'm concating, right, to flatten this tree into one long list, well, something I told you earlier probably conflicts with that, which is that in functional programming, we never mutate anything. We don't mutate a list. So that gives us this weird sort of scenario where it's sort of like, well, we know we don't mutate a list, yet Brad said he's going to concat these lists together to make one big long list. How do you change a list without changing a list? That is where the trick of persistent data structures and functional programming comes in, right? So
okay, gotcha.
one way you could do it is you could clone the list. So I start with a list of 1 item, right? I could make a copy of that list with 4 more items and to make a list of 5, right? I could take this list of what's now 5 and I could clone the whole thing and I can add 16, right? That would work. It would follow the rule of being immutable, right? But it's probably also terribly inefficient, isn't it? Because I'm copying the whole list every time, which is a very expensive operation. So there's actually a better way to do that, where I can both maintain the original list and get a copy of it, right? What we need in here is a linked list. Oh, sorry, I'm not on presentation mode. What we need here is a linked list, which is probably one of those things you may have, if you went to comp sci school, you probably learned about it in school, quickly forgot about it and never used it again, right?
Good old C++.
Yeah. Turns out it's actually useful in situations like this. So using a Ruby gem, we get a linked list from a Ruby gem called hamster, right? So I have a hamster, and I pass it this 1, 2, 3, right? I get back this list, and it has 2 functions, head and tail, right? So head is the first item, that's 1, right? Tail is everything that comes after the first item in this list. You can see that it returns a list of 2 and 3, right? And then it also has this operation cons, and cons adds whatever you pass it to the beginning of the list, right? Which is kind of counterintuitive because usually you're adding things to the end of the list, right? Cons adds it at the beginning, so that given list 1, 2, 3, we get back 0, 1, 2, 3. Now, this is what's special about this data structure, is that I take list 1, 2, 3, right? I do list.cons, which tacks on a 0. When I print the original list, right, to the console, it hasn't changed. It's still 1, 2, 3, right? But I'm sorry, that should say new list, right? But new list is still 0, 1, 2, 3. So I've tacked a 0 to the front of the list, but I haven't modified the original list. You can see that because list still comes out as 1, 2, 3, right? And the way that works is by using references to the linked list, right? My original list points to the node 1, and then when I cons to tack a 0 on at the beginning, my new list variable points to the 0. So in that way, list still points to 1, 2, 3, new list points to 0, 1, 2, 3, but because it's a linked list, I have not actually cloned a list, right? That's the key of a persistent functional data structure, is that you can take it, you can add something to it, get a copy without actually doing any deep cloning, which is an expensive operation. So it's both fast, memory efficient, processor efficient, and immutable. That's what a functional persistent data structure is, right? In this case, our list class.
Nice.
Yep. So just to summarize, just to get the terms right, persistent is immutable, right? But immutable is not always persistent. So a persistent list is one that is immutable, which doesn't clone things when you do operations on them. Okay. So it turns out we're going to use that twice in this program, right? Because one of the other things this program has to do is it has to remember its history. As I traverse through the possible space down the tree of possible moves, I have to keep the history of nodes that I've traveled to, so that at the end I can print out the answer, and so that I don't actually double back and end up on a position I've already been, or I'd end up in an infinite loop, right? So just to show you a little more how I'm going to accomplish that, right? So here I'm using the same list again, right? I've got 4 original band members here, right? I do .tail removes the one on the front, which removes David. .cons adds Sammy to the front of the list, right? So my original list is David, Eddie, Alex, Michael, and my modified one is Sammy, Eddie, Alex, Michael, right? The references at that point look like this, because it's a linked list. The head ones, David and Sammy, can both reference the same tail, right? And in that way, I can have one variable that points to David, Eddie, Alex, Michael, and one that points to Sammy, Eddie, Alex, Michael, without cloning once again, right? Which matches what I'm trying to do with this tree structure. So the vertical one here is it represents the history that I'm going to be keeping as I traverse through, right? Well, the orange line here is the one that represents the order in which I'm checking to see if these moves actually resulted in my little block falling through the hole at the end and winning the game. Right, and you can see that this is this history list is a tree-shaped linked list, right? But using this technique, like I said, right, it's an efficient tree linked list because we're not cloning any of the nodes. Okay, so let's actually look at this program now, and we'll see some pure functional Ruby in action. So let me make this a little bigger. We want about 18. Okay, is that size good enough on that, gentlemen?
It doesn't look like we're getting that screen. Are you on one screen or multiple screens?
Yeah, I'm on one monitor. Hold on. Let me. I know how to do this. Let me share a different one.
Hey, there's JJ.
Oh, hey, JJ. Here it is. All right, can you see it now?
Give it 1 sec. Boom. Got it.
It's up.
Okay, cool. So I start off with a few things here. So what I'm passing in is a string, right? Remember, I've got a string here that represents my level. So that's what it looks like in ASCII. That's an ASCII representation of my level. We pass that in here, and I've got some functions that I won't go into that basically get back a level array, right? They get the start position, they get the end position. And then I've got a function is on board, right? I'm passing it the level array, right? This is a higher order function, is on board. What I'm getting back is a function. Let me show you. You can see that this returns a function. This is a lambda expression in Ruby, right? So I'm passing a level array and getting back a function, whereas if I pass it a position, it tells me whether that is a legal move or false if it's off the side, right? So this is a function, right? I'm also creating an is-goal function, right, where and here I've just done it right in line, right? This takes a block and tells me if I have in fact reached the end of the level, right? So here are two higher order functions, which is one of our functional techniques, right? So I get a start block here with this block function, and this is a common structural or functional technique. So see this function block here? It takes well, let me start with position, right? You've got this one pause, right, which takes a row and a column and returns a struct, right? And you've got one block that takes 2 positions, pauses, right, and returns a struct with A and B. So it's these are basically kind of like factory functions, right? Where we're taking in 2 values and just returning a struct that contains those 2 things. A real functional language would use a tuple here, but Ruby doesn't support tuples. But this is a common functional paradigm you see of making simple functions that return, that take simple values and return more complicated structures. Then I have a starting move list, right, which is, I won't get too much into this because I can't go through all of it, but let's just look down this, right? So I've got my two data types right here, a position and a block. I've got my functions is on board, and one of the interesting things about representing the board as a function is that you can do this, an infinite board, just by returning true, which is kind of cool and great for unit testing. And now you can see that I've got some functions left, right, up, and down. So these are going to take a position, which is just y and x, right, and returns it moved either left, right, up, or down. But the important thing to realize here is that we're not mutating that position struct, right? Because this pause function, right, is this factory function over here, when I call it, I get back a new struct every time, right? That's the important part here, is I'm not mutating that data structure, right? So we're adhering to functional programming by not mutating anything. In fact, the way you know this whole program is pure functional is that I never declare something as a variable and change the value, not once. There's not a single mutation in this whole program. There's also not a single loop in the whole program. I've got a few other functions here. I pass in a block. It tells me if it's standing up, lying down. I've got ones that move left, move right, move up and down. But once again, they call my factory functions block and pause, which means we're getting a fresh copy. We're not mutating anything. So let's look at the actual solver here. There's some stuff in here that finds legal moves, that tells you if you've already visited stuff, right? I'll skip past those. And here's the important function, right? This move sequence function, because this is the one that does that tree flattening algorithm that I showed you with my graphics. So we take a list of moves, right? We take the isOnBoard function, which tells us, make sure we're not falling off the end. And we're taking, when we start with that moves, here's our flat map, just like I told you we're going to use. We take the list of moves, which are basically like the levels of the tree. So if I've, as you may remember, we start off with a list of one item, then we get 4, which is the first row in the tree, then we get 16 is the second row in that tree. That's move lists, right? So starting with 1, we're flat mapping to legal next moves, which could be up to 4 moves, right? And we get back the next tier. So there's our flat map, right? Then here's our concat, right? Which is where we're taking our existing moves and we're adding on the list from the next tier, right? And this is our lazy function, right? If I take this out right here, notice that this is the recursive call, right? So move sequence is calling itself, right? So there's a recursive call, right? Which is why it's recursive breadth first tree traversal. But if I run it just like this, what happens is it calculates all of the possible solutions to the formula, right? In other words, if there are 100 possible ways to win the level, it will calculate all 100, right? Which is not what I wanted. I only want the first. So by adding in this extra little block here from the hamster library, this gives us a lazy concat, whereby I have a moves list. This function move sequence is going to return that list.
I like that. That was nice.
Yeah, and when this concat, right, is a lazy concat where it will not actually call this inner recursive call unless I actually explicitly ask for it, right? So this is sort of the secret sauce whereby instead of calculating the whole dang tree, which could be enormous, I can only get one, right? So this function, in other words, it returns a lazy evaluated sequence of a flattened tree of possible moves of my block, right? Well, how do we find the answer then, right? I've already got the sequence here. It hasn't been evaluated yet, but as I iterate through the sequence, it's going to actually flatten out that tree. Well, you find the answer the same way you would any other thing, which is select, aka filter, right? Here's my sequence. I call the filter operation on it, depending on using my isGoal function to tell me if I've reached the end, and I get a solution, right? One of the interesting things is this solution right here, this is a sequence, it still has not been evaluated. This solution's this list that I get back represents the answer, yet I still haven't actually run anything. I have to call .first to actually run it. Now we actually have the first solution. So, if you've used Python, C#, whatever, you're probably used to sort of these lazy sequences, etc., right? We're used to things like first to get the first item in the list. We're used to select, aka filter, right, to pick the items we want out of the list. But when we add that with the laziness, That's really, really cool. It allows us to take what's basically an infinite algorithm, right, and then make it not infinite and allow us to find basically the first answer, the first thing we're looking for. Very, very cool. Very, very, very efficient. So that's how it works. Do you guys do you have any questions about this program?
Not so far.
No, it's gorgeous.
Yeah, it looks really good.
Thank you.
And there you go, the higher order function, Brad Urani.
Yeah, there we go. Here's the higher order function right here. Select or filter.
Nice. Yep. No. I like that, how you introduced the lazy and then moved on to show, how you can not be stuck and how to keep it clean and fast. I like that a lot.
Yeah. So this program actually won't if you take out the laziness, actually it won't hit an infinite loop. It will just calculate every possible way to win the level, which is not infinite because a lot of moves end up off the board, and we've got protection in there to keep you from evaluating a position you've already been in, right? So that's why it's not infinite. It's just really, really slow if you calculate every possible solution. This is really, really fast because it only gets the first one. But it's cool because you program it as if you're trying to get all of them, right? Which is an easier way to program it than trying just to get the first one. Imagine trying to just get the first one using procedural code. That'd be a headache. This way, you're basically writing a pure, nice, recursive tree traversal thing that, in most circumstances, would be infinite, and it allows you, using laziness, to only evaluate up to the first answer, which is very cool. So let's see it in action one more time before I sort of. Let me summarize a few things just to notice about this code. Once again, just to go through them. We've got higher order functions. We know that's functional programming. This function returns a function. This is a function assigned to a variable. We've seen higher order functions here. There's not a single mutation in the entire program. We use our factory methods to return new objects every time, so we're sure not mutating. And we've introduced laziness to solve a recursive algorithm. Awesome. I want to show you another level here because this level is real fun, right? So this block, it has to.
You're gonna have to. Don't forget, you're gonna have to swap the screens real quick.
Sorry. Hello again.
Hello.
Where is that? How do I get back to blocks first? Oh. There's that. So this level is kind of cool because that X down there makes a bridge, right? Well, do you really need it? Maybe there's a way to solve this. Without actually hitting that X first.
Yeah, that's interesting because that's a different variable that it has to account for, correct?
Right. Well, my program does not simulate the little bridge and all that kind of stuff. It'd be cool if it did, but it doesn't. But if I actually run the solver, I don't want to go through like switching back and forth between the screens here. But
no, you don't
if I run the solver, if I run the solver, that in this form this level is on, right? It can't actually get to the goal. Can you see my console next to my web browser here?
No.
Nope.
Okay. Okay. Well, I'm going to skip this. It's too hard to do during the podcast. But using a solver, I proved that to get to the goal, you do actually have to go and you do have to hit the X. You have to be standing right up on it. That creates a little bridge. It creates another piece like way down in the corner of this void over here. You can see my pointer, right?
Yes.
Okay. It creates one block right here where my pointer is, right? Then you go back over that block, and then you can get to the end, which is a pretty cool thing that I proved with my program. So what do we learn at the end of this? Let's see. So like, where do you use this? This is sort of a contrived, sort of academic example. Can you see my screen again?
Yes.
My slideshow. Okay. This is sort of a contrived example, right? Most of you aren't solving problems like this day in, day out. So where is functional programming actually useful? It's in your business logic. It's in your algorithms. It's in the logic-heavy, intensive parts of your code. So a good way to code, right, to use these functional techniques I showed you is to have your program have basically an object-oriented shell, which is like the interface, possibly the domain model, like your models or something, like if you're in an MVC-type framework, right? And to have a functional core in the middle where you use pure functional programming in your logic, right? So a web application, for instance, think of this as a transformation where the request, your query string variables and stuff that comes in, or your input, right? You've got your shell of controllers, and then you've got a functional business layer that does basically a transformation, gets you your view model, right, or your data that you need to display the page, That's a good way to. It's great in web applications in that sense. You've got your ORM, which is active record. You've got your controllers, in your MVC framework. That's OO, and you've got a functional business layer in between. That's how you can use functional programming in your daily, day in day out things you're doing. So we've shown that we can functional programming in Ruby. So what's the point? Do we need all these functional fancy languages like Clojure and Scala and Haskell, which are quote unquote pure functional programming? I would say yes. Ruby, Java, C#, they're all still missing some features. They're all real close to being good functional languages, but they're all missing a few things. Pure functional languages, the only one of which I know of is Haskell, is useful but for a narrow set of problems. What I mean by pure is that in Haskell, you actually cannot mutate a variable. It's built right into the language, that you can't assign something and then change it. Enforced by the language, right? I like hybrid languages like Scala and Clojure. Even Martin Odersky, the inventor of Scala, said, I think Scala's object-oriented features are more powerful than its functional features. The best languages, in my opinion, have both. And they are, if you want to write this type of code, they're worth looking into. So what did we learn? Put all the state in one place, use as little stateful code as you can to get the job done. In my Blocksters program, the only state was the level, was that original string I made, which was an ASCII representation of the level. Right? Then we just passed it through this pipeline, but nowhere in that pipeline did we, set any variables that we were changing or anything like that. So all the state was in one place. It was only in the input, right? Immutable data structures give peace of mind. You can imagine that program I showed you, if you wanted to convert it to execute in parallel so that you could solve the problems faster, it'd be really easy to parallelize because there's no chance of getting deadlocks or race conditions, right? Recursion and linked lists are the way to do list operations. That's so that we can use those persistent data structures so that we can have immutable lists that are also performant, right? Lazy sequences are very, very powerful. They allow us to write the code without worrying about, how much of it's going to execute, about evaluating huge amounts of stuff we don't need. And then higher order functions, they lead to shorter code, more concise code, just plain better code, more testable code. That code is on GitHub if you want to check it out. Follow me on Twitter. And then I highly recommend that course. I think they're going to be teaching it soon. It's on Coursera, Functional Programming in Scala, in which you'll be solving that Blocksters program yourselves. Highly recommended.
Awesome.
So
boom!
That concludes
Drop the mic and walk away, sir.
That concludes the formally prepared part of my talk.
So, do you get a lot of questions about the MVVM and different stuff like that about how people want to approach it from those type of angles as opposed to this route?
Yeah, interestingly, MVVM is a concept that doesn't exist in the Ruby world. That's one I stole from .NET MVC, Microsoft world. Although it's unfortunate. What that means for you viewers out there is, you've got your typical MVC application. The data comes into your controller. You get a model. You can pass the model right back to your views. I don't recommend it, right? Usually you're going to want to do some transformations, combine some things from other tables, etc., right, and pass that back to your view. In Ruby, you typically use a hash. That's what we mean by view model. So that, that does. We use exactly these patterns. We write our Ruby on Rails a little differently than most people write it. In that, we've got OO on the ends. Active record, our ORM is very OO, and the Rails framework itself is very OO. But we've got a lot of layers in between where we use functional programming, where we're basically passing back and forth, hashes, right, using functional style. And we found it cleans up our business logic. Way more unit testable. We unit test all our business logic, and having those pure functions, right? A pure function is a function without a side effect, where we're not mutating a variable. In other words, it takes parameters in and returns a result and doesn't mutate anything right there in the middle, right? By writing pure functions, it's really easy to unit test a pure function. So we design code in ways, for instance, so a web request comes in, say I need to query some database tables. I try to do all the querying up at the top, right? Because that's kind of messy to test, right? Because you have to mock out the calls to the database, etc., right? For a unit test. I try to get all those out of the way, right? Pass whatever I get back into the functions that do all that business logic, and those business logics are written in a functional way, in a way with pure functions, and that makes it way easier to test. When I'm not mixing my database queries in with my business logic, it's really, really easy to test the business logic. Right, which is a huge benefit. Making a database query, by the way, is a side effect. If you're wondering, right? So yeah, that's what we go for. That's how we do it at Upside.
Nice, nice.
Cool,
Gus,
cool, nice.
do you have any particular questions that came up maybe during the demo, or any questions on this functional programming using this model?
There's tons of questions that I have. I'm just going to shoot from one from the hip because I know I'm going to be asked it tomorrow or the next day. So functional programming kind of removes the whole object-oriented piece out of the picture. Even though it doesn't, I mean, you are, but you aren't, right? You're not type-basing it. Why do that, and what is the number one bonus for doing that?
Right. So I use object-oriented and functional programming together in the same program, just not really in the same classes, right?
Mm-hmm.
Just to be clear, like functional programming is not attempting to replace OO. It replaces procedural programming, right? Which is all your for loops, basically.
Exactly. Yeah.
Why do that? Basically, for the reasons I said, when you start stringing together higher order functions, there's less room for error. Think back to that the Java implementation of isPrime and all the little variables it set. You get into crazy problems like forgetting to reset variables. It's harder to unit test. If you've got an object with a method that is mutating a variable that's in the top of your class, right? It's kind of hard to unit test that kind of stuff. But you'll find when you write code where you're very, very, very careful about minimizing the mutation of state, that leads to fewer mutations of state, which leads to fewer bugs. You know what I mean? By chaining together these higher order functions, all these commands, you end up with first of all just plain shorter programs. And if you've ever switched from Java to Scala or C# to F#, the programs are like 3/4 as long. Less code, fewer bugs. Simple as that. And it's also more testable. So
yeah, I liked how you were able to set those too, and I like not messing at all with the original content. It makes a lot of sense to me.
That was nice, wasn't it?
Yeah, because think about if you had so in that list example, you have a list and it starts with a few values. Let's say you pass that off. You're passing that by reference. So you pass it to some other class, right? That may mutate the list, right? If you're passing that by reference.
And then everything's going to be jacked from there on.
Now you get it back. You may not know that when you passed it down that it got mutated by something else. You may expect it to be the same, and if it's not, right, then you've got trouble. So by forcing immutability, you prevent other functions, because you may be passing it to another library, you know what I mean? You may be passing it to code that someone else wrote, and they may be mutating it, you don't know, and so you have no idea when you're passing around references to a list what else has changed the list between when you pass it off and when you get it back.
Very true.
So that's an important point, and that goes double if you're talking about multi-threaded code, right? Because different threads can all mutate a list all over the place.
Yeah.
You know what I mean? And that's when you get your big bugs. That's when you get those race conditions, the deadlocks where the program just freezes. That's big trouble. So immutability is it's almost de rigueur now if you're writing multi-threaded code to use functional programming.
No, it was really gorgeous, and I'm really glad you showed off the demo. Again, Brad, it's amazing to have you on. That's at Brad Urani, Urani, on Twitter, and fractalbanana.com. That's I like that. It's pretty intense right there. I'm not gonna lie.
Amazing.
So, what's next for you? Like what are you doing? Where can people continue to kind of follow what you have going on?
I've been busy. I lead a team at Upside of wonderful developers that I couldn't be happier with, that we got from Launch Code. We're deep in startup land. Upside is this financial tech startup where I work. We've only got 10 people, and we're trying to change the world with personal investments, and that keeps me busy, but not so busy that I don't have time to mess around with other things. I'm doing a lot of JavaScript. I have the same version of this talk, exactly the same talk, except done in JavaScript, that I gave at the St. Louis JavaScript meetup. And I'm going to try to be giving that at the Kansas City Developer Conference. If, cross your fingers, they accept it, I'd love to give that talk again at STLJS, at KCDC, the Kansas City Developers Conference. I'm very interested in JavaScript. We use Ember.js, which is a big single-page app framework. It's the competitor to Angular, basically. We've been using that, and I really, really like it. But I also think it's really interesting what Facebook is doing on the JavaScript end with React.js. React follows more closely this functional paradigm that I've just explained to you all, bringing it to front-end web development. And I was tempted to explore it before. Instead, I chose Ember because React was still pretty new. Now it's just like all the cool kids are like jumping to React, and it's for exactly the reason that I explained in that they use immutable data. I'm pretty sure about that. They have explicit state changes. They've got one model for your entire page. It gets passed through a functional pipeline. So I think that it's possible. I haven't tried it yet, but I'm really tempted to try that and see how that changes the faces of front-end web development using the techniques I just showed you.
Well, I gotta say, Brad, I'm not worthy, brother. I'm not worthy. Awesome, great talk, great to again have you back on. If you want to talk about anything, don't forget to come back. Gus, any final thoughts before the end of the show?
No, actually, I think functional programming is one of those things that a lot of people overlook. We also have F# out there for some people who are hitting that. Not that I'm saying that anything is better or worse. But it's nice to know.
Gus, I'll say it's better.
Okay, you can. You're closer to it than I am.
I think one of the biggest shames. I think one of the biggest shames in Microsoft land is that people are still on C# and haven't moved to F#. Actually.
Yeah, it's kind of surprising, isn't it?
Yeah.
But there's a lot of people that are proponents for functional programming of any kind, right? And then F# on top of that, if you're in the Microsoft realm.
Yeah.
There is no perfect answer to anything. Which is really
true.
cool because that means we can play and have fun and do a lot of cool things. But that being said, I think F# is way overlooked and shouldn't be.
Oh, I absolutely agree.
Yeah, and functional allows us to do things that other people that we couldn't do before. So keep going out and praising it, Brad, because we need more people to tell the story.
Will do.
Awesome. Well, again, Brad, thank you so much for being on the show. It really means a lot to us. And Gus, as always, thanks, brother man. People can find you at in_F_E on Twitter. You can also find him at Cosmic Coding. I believe that's .com, if I'm not wrong about that. Awesome. So, again, thank you, Kevin, for all your work from behind the scenes. Everybody, don't forget to follow us. Follow the show on YouTube. Go to our website, codecaststl.com, and hit us up on the web. Tell us what you want to see and the guests that you want you want to see presentations on. We would really appreciate that. So from the entire CodeCast crew, good coding. We're out.